The purpose of today's activity is to find the coefficient of static friction between two materials. Now, what two materials are we going to use? In the last lab that you did, you got to choose the materials that you were using. Today you don't. Today you're going to find the coefficient of static friction between a wooden block, in fact, the same wooden block as you used in the last activity, and a plastic ramp. This plastic ramp. Everybody's going to have the same ones. And therefore, theoretically, everybody should get the same coefficient of friction. Remember to phrase your problem in the form of a question. And remember, a question always has a question mark at the end of it, unlike some of you in the last lab who wrote, what is the coefficient of kinetic friction between blank, and then put a period after it. Phrase in the form of a question with a question mark. Okay, variables. I'm not going to tell you what the variables are. You'll figure that out as we go, but I'll throw some hints out there. Remember, though, that we only need, in fact, not only do we only need one manipulated variable, we can only have one manipulated variable. Control variables, there's an infinite number of control variables, but you don't need to list an infinite number of them. You list 2 or 3 good control variables, the really, really important ones, and I'll give you full marks for your control variables. These should become fairly clear as we go through the materials and the procedure. All right, here's what you need to use. First of all, a triple beam balance scale, and you can imagine what you're going to use that for, right? To find the mass. If you have trouble using the triple beam balance scale, let me know and I'll help you find the mass from that. What else you need to use? Well, you need your wooden block with the mass set. You also need a plastic ramp. And you also need your phone. Now, the phone that you see here is an iPhone. It has a compass built in. And that compass will allow you to measure angles of incline as well. If you have an Android device, I don't know that it has it built in, the app built in, but I do know that you can download an app that will do the same thing. Regardless of whether you're using an iPhone or an Android device, all you have to do to find the angle of incline, okay, which of course we're going to want to find on this angle of incline right here, is to set your device on there. Okay, make sure you're holding it so it doesn't slide down itself, and then read the value off. You can see that the value right here is 10 degrees. So we would say this theta right here would be 10 degrees. Make sense? That's your materials. Now, how are you going to actually do this? Well, what you want to do here is gradually increase the angle of that incline until the wooden block starts moving. When that happens, when it starts moving, you know that you're going to have an F parallel that has to be equal to the max force of static friction. This thing starts moving when the applied force meets the maximum force of static friction. What is my applied force here? Well, because I'm increasing the angle of the incline, my applied force is my F parallel. So how do we find the value of F parallel so that we can find FSF max? Well, you guys know this as well. This is the force of gravity acting down. This is the normal force acting perpendicular to the surface. And we know that F parallel ends up being parallel to the surface and perpendicular to the normal force. This is nothing new, right? This is stuff that you've done over the last several days. This angle of incline is what you're measuring with your iPhone. This is going to be the same angle that you're measuring with your iPhone. Now you're able to find the maximum force of static friction. So you're going to increase the angle of incline, measure the angle at which it starts moving, and of course you're going to measure the mass of the block of wood and the masses that are on it when it starts moving. Then you're going to repeat that by changing the mass, changing the normal force. See what angle it takes to cause it to slide down now. Increase it again, see what angle it takes. Increase it again, see what angle it takes. Ultimately, you're going to get a data table that looks like this. The mass of the block and the angle of the incline at which it starts moving. You're going to do 10 trials, at least 10 trials. So 10 different masses and 10 different corresponding angles of incline. And then we want to figure out what Fn is and what FSF max is, because that's what we're ultimately going to plot here. So let's go back to my drawing again. Here's the object, okay, the wooden block. Okay, here's the angle right here. We're going to say that this is the force of gravity acting down. We're going to say that this is the normal force acting perpendicular to the surface. And we're going to say that this is FSF max. Sorry, this is F parallel, which of course is going to correspond to FSF max. So how do you get the normal force? Well, the normal force is the adjacent side of that triangle. So we're going to find the normal force by saying cosine theta is equal to Fn over m times g, or Fn is going to be equal to mg cosine theta. The maximum force of static friction, well, because it's the same value as F parallel, we're going to say sine theta is equal to F parallel over mg. F parallel is equal to mg sine theta. And then plug that value in here. Because again, F parallel is equal to the maximum force of static friction. Then what do you think you're going to do? Plot a graph. Okay, plot a graph of responding variable versus manipulated variable. On your graph, you should see FSF max on the y-axis, and you should see Fn on the x-axis. It should be really close to a straight line. Get your slope. And to do the same analysis as we did last time. Y is equal to mx plus b. The y-axis is FSF max. M is the slope. X is the normal force. And there will be no y-intercept, or at least it'll be close enough to zero that you can drop it. That's from your graph. From your data sheet, we'd say FSF max is equal to mu times the normal force. Then we start crossing things off that appear in both. And we're left with the slope is equal to mu, which of course is what we want to find here. So the slope of FSF max versus Fn is equal to the coefficient of friction, just like it was in the last time, but this time it's a little bit harder to find the values of FSF max and the normal force. Last time it was either just read the value off of the scale or do a simple calculation. This time we got to do a little bit more. Mg cosine theta to find the normal force, mg sine theta to find F parallel and therefore FSF max. Yep. Once you have your coefficient of friction, well, it's time for your conclusion, right? The coefficient of friction between plastic and wooden block is blank, and then this is how I know it. And then, of course, your sources of error plus your suggestions for improvement. Usually 2 or 3 good sources of error, 2 or 3 good suggestions for improvement. What do you got to hand in for this? We got our problem. We have our materials or our apparatus. We have our variables, procedure, data, analysis, and then sources of error. That's the only thing we're missing here. Oh yeah, conclusion, yes. That's not what I meant. I meant to leave out one thing. I didn't mean to leave out conclusion. What do we leave out? Well, usually you'd have a hypothesis, right? But it doesn't make sense to have a hypothesis when you're finding a number, right? Which is would be more of a guess as opposed to a hypothesis. If the problem of this lab was to find a relationship between 2 variables, then a hypothesis would absolutely make sense here. But if it's to find a number, it doesn't make much sense to do a hypothesis. Yep. All right, I'm going to have you form your groups again. And remember, as you're completing this, that you are not, you shouldn't get random data. You shouldn't get data that's scattered all over the place, sometimes increasing, sometimes decreasing. But the relationship that you see between the mass of the block and the angle of the incline before you do any number crunching with it may not necessarily be what you expect. So don't panic about that. If this looks different than you expect it to look, don't sweat that. If your data points, as I say, are all over the place, well, then you might want to take another look at your data. There should be a pattern, but it's not necessarily going to be the pattern that you expect to get.